Okay, so this is another handout that we would typically kind of go over in class. So I thought I would try to run through it here online. And so what it is it's trying to incorporate both the concept of absolute age dating and relative age dating, because ultimately we want to use those together to get the best picture of what occurred in the past. So with as much information as we can tell a more accurate story. So the couple things that you're seeing here is this is another side view, right? So we're looking at a slice into the earth. And you want to note that you're seeing a couple different things here. And so what this layer here at the bottom is what's called a granite. You've probably heard of granite, but in case you're unaware, granite is an igneous rock. And so it was molten at one time, and then it's cooled and crystallized. We do certainly have this layer here that we're kind of concerned about, what we want to figure out the age of. And this is another igneous rock. And you can see there's some baked zones on either side of our igneous rock. And then there is a third igneous rock here, and it's layer E. And layer E does have a baked zone, but it's only on the bottom here. And so we want to use all of this information to figure out what's going on. And we could. If I asked you to put these in order, so you have a granite, B, E, C, and A, using your relative age dating principles, you should be able to do that. And so when we're trying to puzzle this out, we can see that A cuts everything. So that suggests it is the youngest because all the units had to be there in order to be cut. So if we look at the bottom here, do we want to say that this is the oldest and then this came in? Or was there a bake zone? But without a baked zone, that suggests that when this material was molten, B did not exist. If B did exist, there would be a bake zone, a contact between B and the granite. What that means is the granite cooled and intruded other rocks that have since been eroded and weathered away. And so we have our granite, and then the sandstone was deposited on top of that at or near the surface. And so that would make the granite the oldest thing here. And then the sandstone came on top of that. So sand was deposited, eventually turned into sandstone. And then do we put C or then E? Well, because there's only a bake zone at the bottom here and not at the top, if this was molten at one point because it was igneous, no baked zone on the top suggests that C was not there to be baked. So the order would suggest the granite, the sandstone, and then a lava flow flowed onto the surface, baked everything beneath it that it touched, hence the bake zone. And then later on, more material was washed in and deposited on top of that and buried it, and eventually turned into a rock, layer C. And then finally, it was cut by A. So granite, B, E, C, A. Not too bad. Hopefully you can explain why you chose that. The other part of the exercise was to get some numbers. And so this parent-daughter story is in class, we'd give out little pieces that represented atoms. But we would say, look, given your number of atoms here, you have 15 parent and 15 daughter. What we want you to do, this is, let's say, the numbers that you would get after you ran your sample through a machine that counted the number of parent and daughter atoms. And we want to figure out how many half-lives have occurred. And our half-life that we're using for this system is 50 million years. And so a lot of times when we first do this, when we're first introducing the idea of absolute age dating, people are a little confused about where to start. But the idea is that you always start the same way. When this rock was first crystallized, the assumption is that there is absolutely no daughter product present in the mineral that I am examining. And so everything, parent, and all the daughters that were created since this rock was born had to all be started out with parent with zero daughter product. So that means that all of these 15 that are now daughter did not exist. They were parent, but they turned into this over geologic time. And so we have to take these 15 and add them back to this to get our starting point, which would be 30 parent and 0 daughter. All of the samples that I'm going to test have to start out with 0 daughter, and I choose the particular mineral that I have knowledge about, that I know that when it was formed, there was no daughter product in that mineral. But over time, we can create that from the decay of the parent. So, if I have my starting point of 30, of course these numbers are just silly that they're so small, they'd be in the millions and higher, but we're just doing this for simplicity. 30 parent, 0 daughter. That's what it was at time 0. So after 1 half-life, what would I expect the count to be? Well, what does that mean? Well, a half-life is just the time it takes for half of the number of parents to decay into daughter product. Well, if I have 30 and half of it is 15, the count after 1 half-life should be 15 parent, 15 daughter. That means that this example here is telling me that 1 half-life has transpired when I found this rock in the field and brought it to my lab and analyzed it. And because I'm analyzing for a particular system that has a half-life of 50 million years, that would mean that 1 half-life has transpired, and that half-life takes 50 million years. So this rock would be 50 million years old. If I counted 2 half-lives, then the rock would be 2 times 50, 100 million years old. 3, 150. And my count would be different. But here, it just shows that only half has decayed. So that's a half-life. We got 1. We know the age of A. How can I use that to help me figure out some other things? Well, we could say, let's use this to figure out what's the age of layer C. Well, look, I don't know the exact age of layer C, but if this is 50, C would have to already be there for A to intrude it. So that would mean C is older than A, older than 50 million years. And so I know it didn't just happen yesterday. It has to be older than 50 million years. So what about E? Well, E brackets it because E is older than C, and C is 100 million. So although I don't get an exact age for C, I can get a better idea of its age by bracketing it. It's between 50 and 100 because I have these two numbers and I can use that to tell me the age. What's the age, if we're following along with this little questionnaire here, right? What's the age of B? All I know is that it's older than 100 million because it existed when this layer was deposited on top. A doesn't really help me with that, give me any closer to the exact number, but I certainly could say that B has to be older than 100 just because of its order. So you don't always get awesome, things out of it. A lot of times we're using it. Number one, it does tell us the exact age of this layer, but then we can use that to help us at least narrow down some of the things, right? At least I know that this event hasn't occurred in the last 5 million years because it can't. The youngest thing here is 50. Everything has to be older than 50, right? So we can help us with that. There's a couple other examples I did here. Let's see if I can grab a couple. We give different sequences here and different times. What I just want to show for this one here is the absolute age stuff. Right, so the other one was pretty easy because it was just the 1 half-life. But look, we could play that game again here. And so when we get the sample here, this is what it was today. I picked it up off the ground, I brought it into my lab, I analyzed it. It told me there was 5 parent atoms, 35 daughter atoms. What do I know? I know that my mineral started out with 0 daughter, so every one of these 35 atoms had to be a parent when the rock was first born. So I add that back to my 5, and my starting point is 40 parent, 0 daughter. What does the count look like after one half-life? We take 40, half of that. So after one half-life, I should have 20 parent, 20 daughter. And that would mean that one half-life has transpired. If that was what I saw, if I saw that I had 20 parent and 20 daughter, that would be one half-life. And the half-life of this system is 700 million years. That would mean that this rock would be 700 million years old. But I don't have that count, so I know it's more than one half-life. And so what I do is I go back to my parent, which has 20, and say, what if I take half again? Now I would have 10, and those additional 10 would transform into daughter. So my new count would be 10 parent and 30 daughter. That would be 2 half-lives. But that's not what I see today, so I have to keep going. I take my 10 parent and I take half again, and I get 5. 5 parent, 35 daughter. That is the count I have today. How did I get there? I had to take half 3 times, which means 3 half-lives has transpired in order to give me the ratio that I have between parent and daughter today. So if my half-life for my system is 700, that's how long it takes for 1. So I have 3, so 3 times 700, we get 2,100 million years for the age of this unit, or 2.1 billion if you like. But this is how we would calculate half-lives. We're just taking half of the parent. But the trick is you have to know that the starting point is always 0 daughter. So you take all of the daughter count and you add it to the parent, and that is the starting count. How many parent you had and 0 daughter. And then you keep taking half until you get to the count that you have today. You figure out how many times did I say I had to take half, and you multiply it by your half-life for the system, and you get the age of the sample. Of course, these numbers are super simplistic, but the general idea still holds true. And so then we could use that to maybe figure out something here. So our same thing that we talked about before is that we have a nice order here. This is an igneous rock. These other 4 are sedimentary rocks. There's a bake zone on the top and bottom. So I could come up with a relative age. I know E had to be first, then D. And because both D and B are baked, I have to put layer B before A could come in. But there's no direct relationship to C, so there's 2 answers to this. It could be E, D, B, C, and then A is the youngest, or E, D, B, A, and C is the youngest. Now, does my numbers help me here? So what do I know about certain things? Well, the thing is that what I know is that because E, D, and B all have to be there before A shows up, they all have to be older than 2.1 billion years. And that can be useful. If I find fossils in here or something in here, and it's like, what? They're 2.1 billion years old. Maybe that's a problem because we know we don't really see fossils in things that old. Or maybe they're bacterial fossils or something crazy. But the stuff that I find in here will tell me what's happening in the world 2.1 billion years ago. If I had no idea of the age of this layer and I'm finding things, this could have happened a million years ago. But the fact that this layer is here helps me figure out at least that these are 2.1 billion year old rocks and not something that's 10 million or 200 million even. So it doesn't give me, same thing, it doesn't tell me absolutely the age of these sedimentary rocks, but by bracketing it, it can give me some information about what's happening in these layers and how it corresponds to what was happening on the Earth at that time. And of course, I can't tell you much about C because I don't know. It could be younger, it could be older. So if all 4 of these were here when it came in, it would be older. But it could have come in later, and I don't have any information with that. what I would look for is another sequence somewhere. If this is a road cut, I would try to go, somewhere else and look for a road cut, and maybe this layer changes direction, or there's some other relationship that could help me figure out C. But with this diagram, that's all I can get. Okay, so that was just an example of how we can use both absolute and relative together. And so, I don't know, maybe that'll give you a little more information if you're still struggling with how we kind of calculate parent-daughter stuff and the half-lives, right? We're just counting how many times we have to take half in order to get the ratio that we see today when we analyze our samples, okay? So, see if that helps, and if you have questions, of course, contact me.